we can start. Okay, so yeah, welcome back. So we already lost one, so hopefully we do not lose another one in the next break. Now we are at the point going to the deterministic modeling approaches, so considering a large number of molecules or something. And now we also will talk about concentrations and not about individual molecules anymore. I will start more or less a little bit similar to what MolCom said. So just considering what effects we have to take into account when we talk about molecular communication systems. So we already knew this arrangement, having a transmitter and a channel and a receiver. So the first thing we might think about is like, what does the transmitter do? So how are molecules released into a system? I think the most easiest thing, what most of the early papers and still today, because math gets easy, assume is that molecules are instantaneously released from some point in the volume. But then there are also maybe some pulsed release, so let's say sending more symbols behind each other. But also sustained releases has to be taken into account. So especially when we release something from polymeric nanoparticles or something, we will never have something instantaneous. It will take molecules, take time to dissolute from the polymer, and then they will diffuse out of the nanoparticle. Yeah, and there's even more, which is not listed here, chemical reaction or something else. Then also in the channel, it hardly depends on what the channel is, what effects can occur. So we have diffusion, MolCom talked a lot about that. We may have external forces. So for example, when we consider magnetic nanoparticles, we may apply artificially a magnetic force to drag them somewhere. Then we might also have gravity or something else. And yeah, a background flow may happen in a microfluidic chip, or also in the human body due to the blood flow or something. Then we might have also some reactions between molecules. And yes, further other effects which are not listed. So there are so many. I just try to highlight the most prominent ones. And then the next question is how are molecules received? So that is basically the third question. And then there might be absorption by absorbing receiver. There might be some reaction, for example, at the receptors of the postsynaptic neuron. Some accumulation effects, or maybe I'm just having a sensor outside the microfluidic chip, which is just observing molecules coming through. And then another thing I want to talk about, and MolCom already made this hint, is the boundaries. We have to consider those because we can assume that the volume is infinitely large. Again, there many calculations get a little bit more straightforward and easy, but in practice, the channels are bounded. So the microfluidic chip, or also a blood vessel or something else, it has a boundary, and something happens when a molecule hits the boundary, and we have to take this effect into account. Okay, so the key questions here are for me always, which effects are relevant for the application I want to build a model for? That is one thing. And the other thing, which of these effects can be quantified mathematically somehow? And this brings me to a rather general mathematical description of these systems. So the dynamics of such a molecular communication system. So let's define a volume, which is just a subset of Rn, and n is in practice maybe not more than 3, because we have a 3-dimensional system somewhere. With a spatial boundary, which has then one order of magnitude for R less, because let's say when we assume a sphere, the volume is 3-dimensional, and when we just talk about the boundary itself, it's like a 2-dimensional region and area. And then we also have a temporal domain, which is in practice, it starts at some time, so I've chosen 0 arbitrarily, and then it might go to infinity. And now the change of the molecule concentration can be described, so in this space over the time, by so-called partial differential equations. That means denoting the concentration by c, it depends on space and time. So here on a vector of spatial coordinates x and time t. And it contains partial derivatives. That means I have not the derivative of c, I have the derivative of c for t, or the derivative of c for some spatial coordinate. And then we can describe this change of concentration by this equation, which contains here, for example, a term which is just a function modeling some molecule release, for example. Then we have here this part for diffusion, with this is kind of the gradient operator. And then we have a diffusion coefficient here denoted as a matrix, because we might have not an isotropic diffusion, so the diffusion coefficient might be different for different directions. In practice, this d here is mostly assumed to be constant. Then we have a term which models flow, And this flow might include plug flow, turbulent flow, and something which is also very relevant is laminar flow. So already Nunzio addressed this in this talk, how the flow behaves in different regimes. And then we might also add a third term, which is just collecting everything I haven't mentioned before, like drag forces or some chemical reactions. So this is just some arbitrary function here, which may be replaced by some chemical reaction or additional forces. Now we have this PDE, and the question is always like how we derive a model. Yes, we have to solve it, obviously, but two things are missing. And this is like very old theory by Hadamard. It's like to have a well-posed problem and to guarantee the uniqueness of a solution that is more mathematical terms. So, but to find a real solution, we need a set of initial conditions. That means how behaves the system when I start to observe it. And the boundary conditions. So what's happening when I reach the boundaries of my system? Basically, both is the same. So the one thing just says, how does the system behave at the temporal boundaries? And I only have one when I start to observe, and there's no for t infinity. And how it behaves on the spatial boundaries. That is just something I need to solve these equations. And a set of initial conditions might be just defined like concentration C at time 0 is some distribution of concentration in the volume. Then we have boundary conditions, and they describe the behavior of the system at the spatial boundaries. So like what's happening when a molecule hits the boundary. And in a general form, it can just be like a function. So just any function depending on time, on space, and on the concentration, and it has some value at the boundary. So we will come to some examples later. The most significant difference mathematically seen is that derivatives at the boundary are taken into the direction of the normal vector. So it's like I'm always going over the boundary of my system there. Okay, so there are a lot of types of boundary conditions. So I think the most common considered in the molecular communication systems are absorbing, reflective, and partly absorbing. And these are already also the three most common kinds of boundary conditions. So boundary conditions of the first kinds just say, okay, I have a boundary condition for the concentration. So just concentration at the boundary has some value. Very common is, for example, to assume that the concentration at the boundary is 0. That is something which we call perfect sink condition, so that a molecule that hits the boundary is absorbed and it will never come back. The second type are so-called Neumann boundary conditions. So they define a condition for, here for example, for the flux. So for the flux which is going out of my system. And assuming that this flux is 0 would be this picture, and then we would have some kind of perfectly reflecting boundary. So we have no off flux, each molecule that hits the boundary is reflected back. And the third type, it's like the most powerful type, it's boundary conditions of the third kind. It relates the flux of molecules with some function of concentrations or more parameters or so. What we could do, for example, model with that is some partly absorbing boundary. So that means when a molecule comes to the boundary, there is a certain probability that it's reflected, or there is a certain probability that it goes out or to the next system which is attached to that. Okay, so now together, to conclude with this mathematical descriptions part, we need a partial differential equation, an initial condition, and a boundary condition. And this constitutes a so-called initial boundary value problem. And these are very important mathematical descriptions of real-world systems. So it doesn't matter if it's biological, physical, or something else. So it's used basically everywhere. And all these three components have to be there to provide a unique solution to this problem. Now, to obtain a system model for a molecular communication system, assuming that I can describe it with these equations, I need to solve these equations. One takeaway message which come more important to me, especially dealing with practical systems, sometimes the key element is to find a mathematical description, which is more important than finding a solution. Because for the solution you have several ideas and techniques you can apply, but sometimes, especially when you have effects which are where you don't know where they come from, it's harder to find a mathematical description for them instead of solving the description later. So just to give some examples how such mathematical descriptions may look like, when we consider here such a microfluidic chip system where we have kind of tube-like channels where molecules are driven by flow and diffusion. So how would this look like? So the transmitter might be some nano device releasing particles or some injection of molecules somewhere. The channel would be a pipe or a pipe network or some approximation for a blood vessel. And the receiver might be a sensor inside or outside the channel. So what are the common assumptions how we model this? So we would say, okay, our geometry is 3D with a volume, and then this volume is denoted with a vector x in in cylindrical coordinates, just defining the boundaries of my system. Then it's mostly assumed that the diffusion is constant and isotropic, so everywhere we have the same diffusion coefficient. And then a common assumption is also that we have laminar flow inside the channel. That means that the flow velocity assumes has this parabolic shape, which we have already seen in, I think, in Nuncio's talk and also in another talk. So how would the boundary value problem look for that? So we would have a simplified form of the general equation I've shown before, having a term for the injection, having a diffusion term now with a constant diffusion coefficient, and here having this spatial dependent flow velocity. Then assuming that we have a microfluidic channel, so it's a reflecting boundary, obviously, so nothing can go out from these tubes. So we have here a reflecting boundary for the radial boundary, and yeah, we have the z direction, which might be infinitely expanded or long enough to assume that. Another system where I just want to go like how we can mathematically describe it is like synaptic communication, assuming here this presynaptic cell, the synaptic cleft is a channel, and here having receivers at the postsynaptic cell. One common assumption is here, for example, to model the channel just as a 3D rectangular system, and then by applying some further simplifications, most people model this as a 1D diffusion in between, using some boundary homogenization on the right boundary or so. Then, when we want to consider enzymatic degradation, the most forward way to do that is like just assuming uniformly distributed enzymes and that the degradation is fast enough, and then we can use just a first order reaction for that. And then the boundary conditions are in this system the most complicated thing, because so they are formulated for the particle flux, and they have now to contain the reception mechanism of these receptors. So this may lead to very complicated and nonlinear boundary conditions at the right boundary of this system here. That is why I've just written the boundary conditions here as just some function of the concentration, because I don't want it to formulate it out on the slides here. So now let's go for some modeling techniques. So basically we can roughly distinguish between numerical techniques and analytical models or analytical techniques. So numerical modeling techniques have some pros. So for example, they're very powerful, they are accurate, and they have algorithms which are capable to simulate very complex spatially physical problems. And we have also many established solvers, for example in MATLAB or in Python, and there are also powerful simulation softwares like COMSOL. But on the negative side, they may cause high computational load, and I think the most obvious drawback is that we have no analytical description. So we run a numerical simulation, we get a set of numbers, and then we run it for a different parameter set, we get another set of numbers, but it's hard to relate parameters to the output. I think the two most prominent examples for numerical methods are finite element methods, which just divide the spatial volume in sub-elements and then you solve these individual sub-elements. Or finite different approximations that is more based on the partial differential equation itself, and you replace every derivative with a finite difference. And then you can end up in a big system of equation, which can also be solved very efficiently, but it's still like you don't have this perfect relation between parameters and output signal. And then we have analytical modeling techniques, which are, yes, on the plus side, they're very insightful and can be used for further analysis. And we like to do that because we want to use these analytical solutions to calculate further measures, which gives us some insight into the system. And they mostly also allow for efficient numerical evaluation because we don't need any spatial discretization or so. But the drawback is here that they are mostly restricted to linear systems with regular geometry. So yeah, there are also some drawbacks on this side. So one of the most prominent methods or approaches to model things analytically are so-called Green's functions. They are investigated to describe the spatio-temporal dynamics of multidimensional linear systems. And these are exactly systems as we have here. I tend to interpret it as like a multidimensional equivalent of an impulse response. So when we have a ODE, we can derive an impulse response, and then we obtain an output by convolving this input with the impulse response. And we can think about it similarly for the Green's function, just with a spatial component on top. So for example, we can we will see an example how to derive it. But in general, we have the concentration C being the integral. This is now kind of, here we have some initial conditions, and then this is going to the integral with the Green's function to obtain the concentration anywhere in the volume. And for time-dependent inputs, we have not only to do the spatial integration, we also would have to do a temporal convolution to include that. Yeah, the Green's functions are obtained by solving the initial boundary value problem and then doing some reformulations. So the pluses, they are very general, they are well established, having insight and powerful analytical models, and they can be used for further analysis. On the negative side, it's like the solution might be not very insightful and computationally complex if, for example, this convolution cannot be solved analytically. That might be a problem for this approach. And also the Green's function itself might be very complex. Then we have also this transfer function approach, which has been mostly established by my PhD supervisor and his PhD students many years ago. It's basically, we will see that it's similar to the Green's functions. It's just like formulating it a little bit differently, having some pros, but also getting some cons on the other side. It's like it's like a clever sequence of transformation to obtain a system description. And then we describe, here it's in the S domain because transfer functions are like something related to frequency domains. The concentration is just expressed as a transfer function which is weighted by the input signal. So it's like just like classical system theory, and allows also a formulation in the discrete time domain in terms of state space descriptions. And similar to the Green's functions, they are obtained by solving the initial boundary value problem. So you see my point, we will come to the stage that we just have to solve these equations, and then we have to decide which model we obtain. Yeah. It's basically similar to the Green's function. It allows a system description in the continuous time domain and a good evaluation. One trick is when we have a discrete time description, this allows for also the incorporation of nonlinear effects. This is maybe one of the pros. But also here, we cannot obtain a really good system description in the continuous time domain when the system is very complex. But this is a similar drawback for most of the analytical modeling techniques. And basically it brings me to the same thing. When we cannot solve the equation, we cannot derive a model. So both of these modeling approaches are based on something which is called an expansion into eigenfunctions. So I shortly want to explain what this means. It's just like we can approximate a function, so here the concentration, for example, by the infinite sum of basis function here, depending on space, weighted with some expansion coefficients. So we know this a long time for Fourier series expansion. How is this working? So for example, here the black curve might be some concentration distribution over space, here over space x. And I can try to approximate this function just by summing up weighted versions of these simple sine functions. And when I take enough of these sine functions, weighting them with the correct values, then I can obtain the black curve here. And that's basically this idea of this basis function expansion. And the same holds for the temporal behavior. So when we look at the overall behavior here of a diffusive system, it might increase due to the release, and then it will just attenuate over time, because diffusion tends to attenuate there. And we just express this as many of these attenuated functions, just summing them up to obtain the correct one. There's one important assumption in these findings here. It's that the spatial temporal domain is separable. So that means that my volume does not change over time. That is a basic assumption for all these methods. It's already here. So you can see I've just here we have concentration depending on space and time, and here I've written it as an expansion coefficient depending on time, and a basis function depending on space. So this is an assumption that it may hold, but we will also see an example where it will not hold. So now, how can we solve this? And the most classical approach is just separation of variables. And I will show you an example for that. So assume a 1D diffusion process. So the most simple thing we can think of, just in one domain between 0 and A. Then we can write the diffusion equation. It's just a simplified form of the equation also MolCom has shown, where we have one time derivative and here a double space derivative for the concentration. Then we assume some boundary conditions. We need them to solve the problem. So I say at x is 0, we have an absorbing boundary, and at x is A, we have a reflective boundary. So it's like molecules can go out on the left-hand side, but they are reflected on the right-hand side. And we have initial condition for the concentration, and we just assume that we have one impulse of concentration somewhere at t is 0. So just the most simple setting we can think of. So now the starting point is exactly what I mentioned before. The concentration can be expressed as the multiplication of a spatial function and a temporal function. So that is just the idea, to separate this behavior, and it also exploits the assumption that space is independent of time. And now I just insert this into this PDE, into this differential equation, and this allows me to obtain this relation here. And finally, I can decompose this using this parameter alpha. So I just say here, the left-hand side equals to alpha squared, and the right-hand side equals to alpha squared. And then I can obtain two simple ordinary differential equations. And these are, in this case, so simple that I can just solve them by inspection, that we have exponential function for the time behavior. And yes, here, for the spatial behavior, we have just, let's say, the sum of two exponential functions, which is a simple solution to an ordinary differential equation. But now, on this slide here, we still have some unknowns. We have the alpha we don't know, and we have the A and the B we don't know. And this is now the point where I said we need the boundary conditions and the initial conditions to obtain a solution here. So first, the boundary conditions. So when we insert the absorbing boundary at x is 0, we find out that B has to be minus A. And this already makes our here our basis function to A times sinus alpha x. So we still need the alpha and the A, but we know a little bit more. Then we insert the boundary at x is A, and this brings us now to the point that we have, remember, we have here the derivative. So we take the derivative of the sine, it's a cosine, and it has to be 0 at the boundary. So finally the cosine has just to be 0. And now comes an interesting point where this series expansion naturally arises. Because this thing here has multiple solutions for every 0 crossing of the cosine. And this means my alpha is not one value, it's infinitely many. So all these multiples of pi half. And now this shows, the evaluation of these boundary conditions show that we have infinitely many solutions to this problem here. Mathematically speaking, we can also say, coming from system theory, the spatial differential operator constitutes a discrete spectrum. So we have these discrete points of solution which constitutes the spectrum of the operator. And now, to obtain a solution for the concentration, we have to sum up all these components. So now we are indexing them by k, and here we have our solution for the concentration with the sine and the exponential function, and now we also know the alpha. But we still need the A of k. And this is now the point where the initial condition comes into play. The missing coefficients are determined by the initial conditions, and they turn out to be the expansion coefficients coming from here from the Fourier sine transformation. And now finally I can represent the concentration as we have shown it for this expansion just by summing up the basis function sigma and the expansion coefficients y bar here. Now where's the relation to the Green's functions and the transfer functions? So when I take this equation here, I just inserted the AK here again, and when I now insert insert the expression for the AKs, I obtain this here, and the blue part here is then the Green's function. Exactly this. And then we obtain here a relation which is similar to what I proposed for the Green's function, and in this case having the delta impulse, it's easy because the integral vanished due to the shifting theory. It's similar for the transfer functions. I just transform this here now to the Laplace domain, so having this expression here, and then I insert the transform of this exponential function, and this brings us to these first order transfer functions here, and then I just rearrange the system and I obtain the representation in terms of transfer functions. So that is what I wanted to say. So these are also just like similar things, but with different properties coming from the same idea of solving a partial differential equation. Okay, this procedure can be easily expanded to higher dimensions. I will not do that. I just want to note where it's used in the MolCom literature so far. So for example, for 2D circular systems, the shape of the basis functions are then no longer sine functions, they are Bessel functions. This might be, for example, used for the modeling of petri dishes, cylindrical cross-sections, cylinders by adding a C component. And also for 3D spherical, The basis functions are no longer signed functions, they are spherical Bessel functions and Legendre polynomials. And also here they are used for simplified cell models, just assuming them as a diffusive sphere, or sometimes also, say, consider a spherical channel, or the dynamics inside a nanoparticle or so by diffusion. And we can also build rectangular models, but those are not so prominent. So what can we do with such system models? So they provide an analytical description for the dynamics of the concentration and fluxes over time. And they can be numerically evaluated to obtain the concentration at any point in the volume. But what is missing here? So we have not incorporated the properties of different transmitters, so different release types, and how can we incorporate them? Yeah, most obvious by convolution. And most of these models only facilitate transparent receivers, because we have just an expression for the concentration at some point in the volume. And we have not considered unbounded domains, and they can just be considered by shifting the boundary to infinity. And there have been also many solutions proposed for unbounded domains, but I tend to focus on bounded domains here. So, but what happens now if we need an absorbing receiver inside the volume, which might happen sometimes? And so far there's no really comprehensive model to place absorbing receivers in really bounded domains completely. For some spherical geometries, there's a trick by modeling the absorbing receiver by a hollow sphere, and the inner sphere is the absorbing boundary. And what is, if the transmitter characteristics are too complicated and the convolution is infeasible, that might also happen, then we might rely on numerical evaluation or on some approximations. Okay. And what's happening is the considered mathematical description is not separable. So what is, if we cannot solve the PDE, then we might also rely on numerical evaluation, or depending on the system parameters, we can use approximate models. Maybe I go through one of the approximate models I have, because I think I'm running out of time a bit.
I mean, it's 3 more minutes.
Let's see how far I can go. Okay, so considering the laminar flow, and maybe I just catch up what Nunzio already said, we have a problem in this so-called mixed regime. So this comes from the coupling of the R and C components of this laminar flow here, the classical separation of variable approach will fail, because we cannot separate these effects from each other. There are some approximate models around, and an alternative approaches, and that is what I said in the very beginning. Sometimes it's important to find out which effects are relevant for the question I'm asking to the system. And this is exactly that. So now let's analyze my system a bit in the terms of dispersion, so the spatial spreading of molecules in such a tube. Therefore, one might derive such a dispersion factor, which is related to the Piclet number and depends on the flow velocity and the radius and the dimensions and the diffusion. And then one might be able to obtain 3 different regimes. So one where flow is dominant, one where diffusion is dominant, and something in between. So the first 2, there are very good approximations around for that, especially for the dispersive regime. Aris and Taylor have done this approximation many years ago. The problem is mostly the mixed regime, so something in between, and that's mostly the problem. So here are just some pictures how this might look like. So for the flow-dominated regime, when I have just a uniform release of molecules, the shape will not change sufficiently over time. Then here, the lower picture where we have a lot of diffusion, we can see already after a while we have a huge spatial spreading, and we cannot distinguish the release position anymore if we would have placed it here. And for the mixed regime here, we can see we are somewhere in between. So we still have this laminar shape, but we also have a lot of dispersion in all directions. So just to show how these approximations work, we can see the similar scenarios here. So here we are in the flow-dominant regime. At the receiver, we have a clear peak. This coming from this, because the shape is not changing over time. And we can see here this green one. This would be the approximation for the dispersive regime. It's not working in the flow-dominant regime. It's clear. And in the dispersive regime, we can see, okay, the flow-dominant approximation is not working, but the approximation for the dispersive regime is also working very well. Okay, so maybe I go through that and expand 2 minutes or so. So this is about looking into the channel, what's happening there and how we can apply a simplification there. The other is the transmitter characteristics, which are very important and sometimes hardly to incorporate. If we have an instantaneous release at t is 0, it's easy because we have just here this spatial integration with the Green's function. When the transmitter characteristics are more complicated, so time dependent, for example, we have to do both integrals, so one over space and one over time. And this might be unfeasible sometimes. And then what one can do, one can try to introduce a similar measure as the dispersion factor alpha by just, let's say, we analyze what is more important for my received signal. Are it the dynamics of the channel or are it the dynamics of the transmitter? And depending on this relation, we might be able to simplify this convolution to something which can be evaluated analytically. But this is just an idea what can be done, and it strongly depends on the arrangement and on the type of receiver and transmitter here. And now finally I want to show you one transmitter where it's getting complicated, but which is very relevant. So we mostly assume some instantaneous release, and we don't think about a release mechanism really, so a physical or biological based release mechanism. And we also had so far the assumption that the spatial domain is independent from time. And this brings me to a concept which is called moving boundary problems. And they are very common, for example, in the community of controlled release. Because it's like when you're throwing a pill into water, you can see a moving boundary problem because it's getting smaller and smaller while it's releasing its molecules. So these are common models to describe, for example, the dissolution and diffusion from polymer-based matrix systems, for example. And this is a common model for some drug carriers or other nanoparticles. And we can see the problem. So basically we can still describe it with a diffusion equation, but the stress comes in for the boundary conditions. Because we have here now this R of t, which is the time-dependent position of the boundary. So we can think about it when we are starting the release from such a type of transmitter. We have initially, it's full of molecules, and then over time, molecules are dissoluted from the solid core, diffusing to the outside, and the solid core is getting smaller and smaller. And that is this moving boundary we have there. And there, everything breaks down with the assumption that time is independent from space. But for this type of problems, there are some approximate solutions. So, and we have to solve both problems. So one for the molecular release, which depends on the position of the so-called diffusion front, and one for the diffusion front, which depends on time. And yeah, you can already see it here. Those equations are not easy to handle, and these are still approximations, which does not hold everywhere. But I just wanted to give an idea where we might go for modeling more practical systems. Okay, so in many practical scenarios we have also a bounded volume, which is very large, with a lot of molecules inside. And maybe it's well mixed because it's a good thing in the lab to do that. And a large number of molecules in this volume. This allows one cool thing is because we can neglect the spatial dependency. Because when we are mixing all the time and we have a lot of molecules, maybe just the temporal progression of the overall concentration is interesting. That might be helpful. But on the other hand, for practical scenarios, a large number of molecules makes some simulation methods which try to simulate the individual molecule positions infeasible. Then these practical scenarios often exhibit nonlinear systems, time-variant behavior, and further effects which we cannot think of or even describe. So what should we do? We should still focus on these practical systems. I think that's very important. And elaborate suitable models which kind of support this analysis for the design of practical MC systems. Even if they contain simplifications or approximations, they have to help us to answer the questions what we want to know from these systems. Okay, I skipped the summary a bit here because just let's go over to the questions because it just summarizes what I've done. And what I've not discussed but is still important, I have not discussed unbounded domains. I think that is just something I missed in this talk here, and I focused on bounded domains. But there are very good papers and very good summaries of models for unbounded MC system domains. Okay, thank you, and I think we can directly go over to questions, right? Yeah.
I have just two comments about the boundary condition that you mentioned. Just for information, we have proposed kinds of homogeneous general boundary conditions for modeling boundary condition when you have a chain of reactions over the cells. Then we may have some more complicated boundary conditions when we have chain of reactions or these things over the boundary. And yeah, we have, just for your information, that we have proposed this general kinds of boundary condition recently in transaction of nanobioscience. It's about transcytosis at the membrane of the cells. It's a general boundary condition that you can see that we can generalize these kinds of boundary conditions.
Yeah, that's what I wanted to say with this kind of function. It's like you can express anything with these boundary conditions just by making this function for the particle, for the molecule flux into the outside as complex as it's necessary to describe the effects there.
And more complicated than this one is if the d at the left side can be another function, which is convolving with derivation of c, then it can be more complicated than this one. Also regarding you mentioned the existence of receivers arbitrarily located in the environment. We have also recently proposed a semi-analytic method for modeling such systems. We can have any kinds of boundary in the environment, and we started with the Green's function modeling first, but since the geometry is arbitrary, then you can't solve it analytically.
Exactly,
we have proposed kinds of method of moments to.
That will work.
It's a good way of tackling these kinds of.
Because exactly, especially when you have trying to model these absorbing receivers somewhere in a bounded volume, you get a problem because you somehow have to take energy out, and this is always not so easily to incorporate in the equations here.
Yes, but generally, the problem molecular communication system, I think, is that you never, the problem is that you don't know exactly where everything is located.
Exactly, yeah.
But always when we are solving these equations, we are assuming that we know everything. The transmitter is here.
That's what I wanted to say with this going to practical. So maybe we have sometimes to neglect just these spatial positions because we don't know it, because when we have, so Nuncio will never inject just one nanoparticle, it will be millions of nanoparticles for transmitting and receiving, and so we have so many different distances in between there, so maybe it's just enough to not consider the spatial component.
May I comment?
Yeah.
Please interrupt me.
Okay.
First is a question. Can you include some active surface? I mean, if you let's think about the experiment that was discussing yesterday. If you have a surface tension interface, where is included the tension in the equation?
So you mean, so as this happens on the boundary, what we discussed yesterday, for example, then this might all bring us to the boundary conditions. Yeah. So there somewhere is the coupling, and especially as what we considered was this transition between fluid and air media, then you might see this more as coupling conditions because we couple two systems with each other. So we have this bounded domain for the fluid, and then we have might a bounded or unbounded domain for the environment. And then these boundary conditions are more like transitions conditions because the output of one system is then the input of the next system, and there these effects can be included.
Second question. When you say absorbing, fully absorbing receiver, these terms that you always use, are you considering the saturation of the system? Because from what we are trying to develop in the lab is something similar to Murat. Then you have what we use is typically the random sequential absorption equation or Lang equation. that you have a square, centimeter square, then if your surface is attracting and binding, then you have some saturation of the active sites.
Yeah.
So all these equations are something like
Exactly. So this kind of absorbing receiver has been discussed many times in MolCom, also with different properties like saturation or explicitly having receptors or having other effects inside. Yeah. So this was, see it as a concluding word for including all these submodels there.
Because right now what I see is that you just send some palette to the molecule and the molecule just disappear from.
This is kind of the most simple approach, which still is for some system models or so. It's used because it's easy to apply, and many of these assumptions help to make an easy mathematical description. Because saturation is always something like a capacitor, so you have an integral, and this makes things more complicated. So when you just assume that it's a molecule which hits the receiver is eaten directly, makes things for modeling perspective and deriving formulas which you can handle sometimes a bit easier. But I totally agree with you that to go into more realistic and practical systems, these things have to be considered because they occur.
Maybe a connected question, slightly out of scope. I just out of curiosity, are there models that cover, let's say, real physical systems in MolCom, in the sense that, I mean, we can't make materia appear or disappear in the world suddenly. So to some extent, in like a long-running MolCom system, we would have to accommodate for our particle generator, for instance, using material from the surrounding conditions, reducing the boundary in that sense, and on the other side, the receiver kind of extending in size because it might be excreting something or something like that.
I think to some extent it might be able to write it down as a mathematical description, having moving boundaries when things get smaller and harvesting from the environment, and so you can write it down, but I think you cannot solve it.
you want what they call like a digital twin for molecular communication.
Yes.
I was just wondering if there's work you know of.
But sometimes, as I said, sometimes it's more important to write it down, because then you already get a lot of insight when you have written down the formulas, even if you cannot solve them.
Well, I think that the double test, that my prototype, you can simulate, theoretical treat in an analytical way very well. I think that you can do everything you would do from this kind of solution.
And that's good. That's good.
You are well.
You're building suitable prototypes for the simplified models we use.
Because we instantaneously release a plug, then we have not absorption detectors. We have very low concentration of particles, so we have no interaction. We have Teflon walls that are perfect reflecting. We are using cylindric geometry, so it's very easy.
Yeah, it's basically, it's perfect to apply the simplified modeling approaches, assuming all these things like reflective boundaries.
There has been some literature on energy harvesting from MolCom, I think.
Yeah, so Aman has also recently, I think, published a paper on that.
Yeah, I know, like the isolated.
Yeah.
I was just wondering because I mean,
I haven't seen that coupled
at some
to
point,
something.
it's a whole coupled system.
I think Max had the bigger picture in mind.
Yeah.
Perpetuum mobile molecular communication system.
Linked to the gas supply of the electricity generator, which produces the.
Yeah. Because it happens like in synapses, everything is fairly local, so a lot of stuff has to get recycled. There has to be that feedback, but we always care about, we have our transmitter and our receiver. Nothing has to go back the other way in most of the modeling that we do. But of course, if you couple these things together, you put it together that way.
Sorry.
Are there any solved analytical solutions which have been applied with spatial restrictions that vary with time?
So what do you mean with spatial restrictions vary with time? Do you-
Sort of spatial boundaries which vary with time.
Yeah, this was these moving boundary problems I said. There are some solutions around, but you have, so for example, so Higuchi has done this a lot many years ago for these moving boundary problems for spherical systems. And you can make it simpler here because you assume that the moving boundary is coming with the same velocity from each direction, so you can say, okay, it's one-dimensional. But he also solved it for a cylinder, which gets smaller, but I think only in the C direction. I don't know if they added the radial component too, but if you like, I can just send you the papers on these moving boundary problems I have.
Are we getting the bibliography at the end? Because we've
Yeah,
seen-
yeah. You have it here, and yeah.
The problem here is that if you consider the polymer like a sponge,
Mhm.
it just releases the particles and the sponge remains the same volume when you solve the problem or the boundary.
No. So for most problems, so what they assume the particle will stay there, but it means what they assume in these problems is that the molecules which are loaded to the polymer are somehow connected with the polymer. So it takes some energy to take them out of this matrix, and this is this dissolution process. And it means so because maybe the diffusion coefficient inside this matrix might be different than to the outside.
Indeed.
So it takes a bit until the surrounding medium comes in, and then it's kind of clearing these molecules from the polymer matrix, and then they are diffusing out. But the other thing is like with these biodegradable things, like where really the particle itself is degraded over time. This is, so also Higuchi there has done similar equations, but just making it more complicated, having an eroding front, which is again following the diffusion front itself.